Have you ever stood outside on a clear night, looked up at the stars, and felt a shiver run down your spine? That sense of wonder mixed with something deeper, something almost unsettling. Out there in the vast, silent dark lies a universe so immense, so mysterious, that it can make even the bravest among us feel small and vulnerable. We often think of space as beautiful, inspiring, even peaceful, but behind that glittering curtain of stars hides a reality that is far stranger and far more terrifying than most of us dare to imagine. Today, we're journeying into the unknown to explore 30 facts about space that will truly send chills through you. This isn't just a list of interesting trivia. It's a deep dive into the cosmic phenomena that defy our understanding of safety, time, and existence itself. From black holes that swallow light whole to rogue planets drifting alone through the void, from the eerie silence of the vacuum to the explosive death of stars, each of these truths reveals a universe that is as awe-inspiring as it is fearsome. We often go about our daily lives wrapped in a bubble of comfort, thinking we're secure on our little planet, but the cosmos has a way of reminding us just how fragile that sense of safety really is. So settle in, open your mind, and prepare to see the universe in a whole new light, one that might keep you awake tonight, staring up at the sky with wide eyes and a racing heart. This exploration isn't just about feeding your curiosity. It's about connecting with something primal within all of us, that mix of fascination and fear when faced with the infinite. Whether you're a seasoned space enthusiast or just someone who occasionally wonders what's really out there, these terrifying truths will leave you with a deeper appreciation for the strange, beautiful, and frightening reality we are all a part of. Our journey into the cosmic unknown begins not with a distant star or a black hole, but with the very emptiness that surrounds them all. The vacuum of space is not just an absence of air, it is an actively hostile environment that would dismantle the human body in a matter of moments. Imagine for a second that your spacesuit simply vanished. The first thing you might feel is the moisture on your tongue and in your eyes beginning to boil. This isn't boiling from heat, but from the sudden, violent drop in pressure. The liquid in your body can no longer remain stable and instantly turns to vapor. Your lungs, filled with air at a much higher pressure, would collapse violently as that air rushed out, causing catastrophic damage. All of this would happen in the first 2 or 3 seconds. You wouldn't have time to scream or even to fully process the pain. Your body would begin to swell, but your skin is tough enough to hold you together, trapping you in a horrifying state. The most critical clock, however, is the one counting down the oxygen in your blood. Without a fresh supply, your brain would begin to shut down. In just 15 seconds, you would lose consciousness. The entire process is a brutal, efficient deconstruction of life, a stark reminder that every single second we exist off of our planet is a gift of incredible engineering and protection. Space doesn't hate us, it is simply and utterly indifferent to our existence, and that indifference is perhaps the most terrifying fact of all. But even if you were perfectly protected within the hull of a spacecraft, another invisible and far more insidious killer lurks just outside your window. This is cosmic radiation, a constant high-energy barrage that our planet's atmosphere and magnetic field tirelessly deflect. Out in deep space, you are exposed to a downpour of atomic nuclei traveling at nearly the speed of light. These aren't just simple particles, they are the shattered remains of exploding stars and galactic events of almost unimaginable power. When one of these particles, like a heavy iron nucleus, slams into a human body, it doesn't just bounce off. It acts like a microscopic cannonball, tearing through cells and shattering the very DNA strands that hold our genetic blueprint. The damage is cumulative and silent. An astronaut on a mission to Mars would be bombarded with the equivalent of a full-body CT scan every 5 days for the entire duration of their journey. This relentless assault significantly elevates the lifetime risk of developing cancer, causes rapid cellular degeneration that can lead to cataracts and heart disease, and there is growing evidence it can even impair cognitive function, effectively clouding the mind at a time when sharp thinking is most critical. Shielding is a monumental challenge. Lead is far too heavy, and aluminum hulls can actually make the problem worse by causing the high-energy particles to splinter into a secondary shower of even more dangerous debris. The only true solution might be force field specifically, recreating our own magnetic bubble around a spacecraft, a technology that still feels like science fiction. So every astronaut who ventures beyond low Earth orbit is making a profound sacrifice, trading years of their long-term health for the privilege of exploration, all while being silently, invisibly shot at by the universe itself. And if you manage to somehow survive the vacuum and the cosmic radiation, there's a gravitational threat lurking in the cosmos so powerful it defies all earthly logic. We call them black holes, but that name doesn't begin to capture their true nature. They are not just holes in space, they are regions where gravity has won a total, absolute victory over every other force in the universe. The point of no return around a black hole is called the event horizon, a spherical boundary from which nothing, not even light, can escape. But the true horror isn't just being trapped, it's what happens to you in the moments before you cross that threshold. As you fall feet first toward a stellar mass black hole, the pull of gravity on your feet is exponentially stronger than the pull on your head. This difference in force, known as a tidal force, begins to stretch you. At first, it might feel like a gentle tug, but it would quickly escalate into an unimaginable ordeal. Your body would be pulled into a long, thin string of atoms, a process scientists vividly call spaghettification. You wouldn't just be ripped apart, you would be sculpted into a single, horrifying strand of what was once you. Think of it like stretching a piece of taffy, but with forces so intense that every molecule is torn from its neighbor in a precise, linear sequence. For a smaller black hole, this spaghettification would happen well outside the event horizon, meaning you'd be gruesomely dismantled while someone watching from a safe distance could still, theoretically, see it happen. With a supermassive black hole, you might actually cross the event horizon intact before the stretching process begins, offering a few additional moments of consciousness inside a realm where the known laws of physics break down completely. In either scenario, the result is the same. You are reduced to a stream of elementary particles added to the black hole's mass and lost to the universe forever. It is a fate that combines the primal fear of falling with the existential dread of being utterly annihilated, not by an impact or an explosion, but by the pure, undistorted power of gravity itself. Yet for all their terrifying power, black holes are at least localized threats, singular monsters in the dark. But there is a far more pervasive and inescapable force at work, one that is reshaping the entire cosmos and sealing our ultimate fate. The universe itself is stretching, expanding at an accelerating rate, and this expansion defies our most fundamental understanding of physics. Because of this, galaxies unimaginably far away are actually moving away from us at speeds that exceed the speed of light. This isn't a violation of Einstein's law that nothing can travel through space faster than light. Instead, it's the fabric of space itself that is growing, carrying those distant galaxies along with it like raisins in a rising loaf of bread. The farther away a raisin is, the more dough expands between it and us, and the faster it appears to recede. For the most distant raisins, the dough is expanding so quickly that no matter how fast we could ever travel, we could never reach them. This creates a cosmological horizon, a permanent barrier beyond which any event, any civilization, any potential sign of life is forever lost to us. The light from those regions, stretched into useless, low-energy radio waves by the expansion, will simply never arrive. We are effectively trapped in an island universe of our own local group of galaxies, which is all that will remain gravitationally bound as everything else is swept away into the darkness. It's the ultimate cosmic isolation, a silent, inexorable process that tells us that most of what exists is not just unknown, but unknowable. The universe has already placed most of its secrets permanently out of reach, leaving us to wonder what incredible wonders are disappearing over the horizon forever beyond our grasp. While we often picture planets neatly orbiting a parent star, that's not the only way a world can exist. Drifting alone through the unimaginable blackness between stars are the true orphans of the cosmos, rogue planets. These are not merely asteroids or comets, but fully formed worlds, some the size of Mars or even larger, that have been violently flung out of their native solar systems by gravitational interactions during the chaotic early days of planetary formation. Once ejected, they are set on a perpetual, solitary path through the interstellar void, untethered from the light and warmth of any sun. Imagine a planet like Earth, but one where the sun never rises. The surface would be a landscape of eternal, absolute night, where temperatures plunge to just a few degrees above absolute zero. Any atmosphere would long ago have frozen solid, creating a global sheet of ice over a frozen ground. Deep beneath that icy crust, however, there might be a sliver of hope for life. Tidal forces from a massive moon or heat from radioactive decay in the planet's core could maintain a vast, dark subsurface ocean, much like those suspected to exist on moons like Europa or Enceladus. In that abyssal blackness cut off from the universe above, who knows what kind of life might huddle around geothermal vents, entirely unaware that a sky even exists. The true terror of these rogue worlds, however, lies not in their frozen surfaces, but in their silent, undetectable movement. Our solar system is not a static, unchanging painting. It's a dynamic cluster of orbits moving through a galaxy that is itself full of moving objects. A rogue planet, dark and emitting no light of its own, would be nearly impossible to spot until it was already alarmingly close to us. Its presence, even if it didn't collide with anything, would be catastrophic. Gravity is the invisible hand that shapes our solar system. The delicate gravitational balance that keeps the planets in their stable, predictable orbits is precisely calibrated. Introducing a massive, uninvited guest and object with perhaps the mass of Earth or Neptune would be like throwing a boulder into a calm, perfectly arranged pond. The rogue planet's gravity would act as a chaotic disruptor, tugging on the outer planets first. It could nudge Neptune or Uranus into new, wildly elliptical orbits, which would in turn destabilize the orbits of Saturn and Jupiter. That chain reaction of gravitational chaos would eventually ripple inward, threatening to send asteroids careening from the main belt toward the inner planets, or worse, altering Earth's own orbit. We could be flung out into the cold ourselves or pulled spiraling inward toward the sun. The unsettling reality is that such an event could already be underway with an object we haven't yet seen. Its dark approach hidden in the overwhelming blackness of space, a ghost already in our machine. Yet for all the chaos a rogue planet could unleash, its destructive potential is limited to a single solar system. There exists a phenomenon out in the depths of space that operates on an entirely different galactic scale of destruction, a random, universe-spanning shotgun blast of pure energy known as a gamma-ray burst. These are not mere explosions, they are the most violent and energetic events known to occur since the Big Bang itself, and for a brief moment, a single gamma-ray burst can outshine every single star in its entire host galaxy combined. They are thought to be the birth cries of black holes, occurring when a massive star goes supernova and collapses in on itself, or when two incredibly dense objects like neutron stars spiral together and merge. In that cataclysmic instant, they don't explode outward in all directions. Instead, they focus their unimaginable power into two narrow, opposing jets of radiation that scream across the universe at the speed of light. If one of those jets were pointed directly at Earth, the consequences would be beyond apocalyptic. The first wave, the initial gamma rays themselves, would hit our atmosphere and begin to shred it apart. The radiation would break apart nitrogen and oxygen molecules, creating a thick brown smog of nitrogen dioxide that would blot out the sun, triggering a rapid, devastating global winter. The ozone layer, our planet's protective shield against ultraviolet radiation, would be completely obliterated. Then the secondary effects would begin. The energy would ignite chemical reactions in the upper atmosphere, creating a cascade of chemical changes that could lead to widespread acid rain. Any life form on the side of the planet facing the blast would be immediately subjected to a wave of radiation intense enough to cause severe mutations or instant death. The entire food chain, from phytoplankton in the oceans to the largest land animals, would collapse. It is widely theorized that a gamma-ray burst might have been responsible for one of the 5 major mass extinction events in Earth's distant past, specifically the Ordovician extinction that wiped out nearly 85% of marine life. The most chilling part of this cosmic threat is its randomness and its speed. There would be no warning. The first sign of the event would be the wave of radiation itself arriving at our planet. We could be going about our day completely unaware that a star died millions of years ago in a distant galaxy, and its final, fatal scream is just now reaching us, carrying with it the power to sterilize a planet. Our Milky Way galaxy is long past its era of frequent star formation that creates these events, making a nearby burst unlikely but not impossible. And from another galaxy, even a burst from millions of light years away could still have a severe, damaging effect if it were close enough and powerful enough. It is the ultimate reminder that we exist in a cosmic shooting gallery, where a random, invisible beam from the distant past could, at any moment, rewrite the future of all life on Earth. Even as we are pushed apart by the expansion of the universe, our local galactic neighborhood is simultaneously being pulled in another direction by a force so immense it defies comprehension. Our Milky Way, along with every other galaxy in our local supercluster, is hurtling through space at an astonishing speed of over 1 million miles per hour toward a specific point in the cosmos, a destination we cannot see. This mysterious, unseen gravitational anchor is known as the Great Attractor, and it represents one of the most profound puzzles in modern astronomy. The terror it evokes isn't one of immediate collision or fiery destruction, but a deeper, more primal fear of the unknown, the chilling realization that we are being irresistibly drawn towards something we cannot identify, something whose true nature is completely hidden from our view. The story of its discovery begins with mapping the cosmic microwave background, the faint afterglow of the Big Bang. This radiation creates a universal frame of reference, a backdrop against which we can measure the true motion of galaxies through space. When astronomers did this, they made a startling discovery. While most galaxies are moving away from us due to the universe's expansion, our entire local group, along with thousands of other galaxies, has a significant peculiar velocity, a drift that carries us sideways against the overall flow of the expansion. It's as if every river in a vast delta is flowing toward the sea, but our boat and all the boats around us are being steadily tugged by a powerful, invisible current toward a single, hidden whirlpool. This deviation is not minor, it is a colossal motion, and it points directly toward a region in the constellation Centaurus. The central problem, the source of the mystery and the unease, is that we cannot see what is pulling us. Our view of the Great Attractor's core is completely blocked by the dense plane of our own Milky Way galaxy, a region packed with so much gas, dust, and stars that it is like trying to see a distant city through a thick, perpetual fog. This obscuring band is known as the zone of avoidance. For decades, the Great Attractor existed only as a gravitational shadow, a phantom presence inferred by its overwhelming pull on everything around it. The very idea that something with the mass of tens of thousands of Milky Way galaxies could be lurking almost next door, completely hidden from our sight, is a humbling reminder of how much of the cosmos remains invisible to us. Further investigation with telescopes that can peer through the galactic fog using infrared and radio waves has revealed that the Great Attractor is likely not a single, terrifyingly dense object, but rather the core of a truly enormous concentration of mass known as the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is our galactic continent, a vast filamentary network of over 100,000 galaxies, all bound together by gravity, and the Great Attractor is its gravitational center of mass. So we are not necessarily falling into a single cosmic beast, but rather toward the dense, collective heart of our local universe. Yet, this revelation doesn't eliminate the underlying terror, it merely reframes it. The sheer scale of the forces at work is what is truly staggering. For our entire galaxy to be moving at such an incredible speed, the mass required is almost beyond calculation. It speaks to the existence of cosmic structures so vast they bend the paths of galaxies like rivers bending around mountains. We are caught in a flow of gravity that we cannot control or escape, passengers on a ride whose final destination is an epoch away. We are being pulled toward a point in space that, by the time we could ever theoretically reach it, will have been reshaped by the expanding universe itself. It is a journey without a tangible end, a constant reminder that even on the scale of galaxies, we are not truly in control of our own motion, but are instead subject to the invisible, irresistible tides of gravity woven through the fabric of the cosmos. But just as we are subject to these immense, invisible tides pulling entire galaxies, our very experience of reality is not as fixed and universal as we believe. Time itself, the steady drumbeat by which we measure our lives, is not constant throughout the cosmos. It is a fluid, malleable fabric that can be stretched and warped by gravity and velocity, a phenomenon known as time dilation. This isn't science fiction. It is a proven, fundamental prediction of Einstein's theory of relativity that has been tested and verified with extraordinary precision. The faster you move through space, the slower you move through time relative to someone who is stationary. Similarly, the stronger the gravitational field you are in, the more time slows down for you compared to someone in a weaker field. The implications are staggering, effectively meaning that there is no single, universal now that every point in the universe agrees upon. For astronauts aboard the International Space Station, this effect is a measurable daily reality. They are both moving at over 17,000 miles per hour relative to the Earth's surface and experiencing slightly less gravity due to their altitude. These two effects work against each other in this specific orbit, but the velocity effect wins out. The result is that time actually passes a tiny bit faster for them. Over a 6-month mission, an astronaut might return to Earth having aged about 0.005 seconds less than everyone they left behind. It's a minuscule difference, almost laughably small, but it proves the principle is undeniably real. The clocks on the GPS satellites that guide your car have to be constantly corrected for this exact reason. Without accounting for both the speed they travel and the weaker gravity they experience compared to the surface, their navigation data would drift by several miles every single day, rendering the entire system useless within minutes. Now scale this concept up to a hypothetical journey to a distant star. A spacecraft capable of traveling at a significant fraction of the speed of light, say 90%, would become a time machine for its crew. A voyage to a star system 20 light-years away would feel, for the astronauts on board, like it took a little less than 9 years of their lives due to time dilation. They could make the round trip and return home having aged only around 18 years. But back on Earth, over 40 years would have passed. They would step out of their ship into a world where their young children were now older than they were, where their friends and family had lived entire lives without them, and where society and technology had advanced by 4 decades. The psychological and emotional impact of this is almost too profound to comprehend. You wouldn't just be returning from a long trip, you would be leaping forward into a future that is no longer your own. The true terror of time dilation, however, lies in its absolute impersonal nature. It is not an optical illusion or a trick of perception. It is a fundamental property of the universe. Your experience of time is entirely local and personal, dictated entirely by your own state of motion and the gravitational forces acting upon you. There is no master clock. This means that if you were to orbit close to a black hole where gravity is unimaginably intense, you might experience a single hour while centuries or even millennia passed for everyone else in the universe. You would be a living relic, a traveler from a distant past, utterly isolated from the entire flow of history. Your every second would be an eternity for everyone you ever knew. This warping of time challenges our most basic understanding of cause and effect and reveals a universe where the flow of time is not a river carrying everyone along at the same rate, but a vast, chaotic ocean with currents that run at infinitely different speeds, forever isolating us in our own personal bubbles of reality. While we look to the stars for existential threats, one of the most immediate dangers to our modern way of life is much closer to home, emanating from the very star that gives us life. The sun is not a placid, constant ball of light. It is a dynamic and sometimes violently unstable nuclear furnace. Its surface is a roiling sea of plasma, and when magnetic field lines on the sun become tangled and snap, they can unleash catastrophic storms of energy directly toward Earth. These solar storms come in two main forms, often together: the intense flash of X-rays from a solar flare and the far more dangerous, slower moving cloud of magnetized plasma known as a coronal mass ejection. A flare reaches us at the speed of light in about 8 minutes, but a coronal mass ejection takes anywhere from 18 hours to several days to travel the 93 million miles to our planet. When one of these massive eruptions is aimed directly at Earth, it doesn't bring physical impact or heat. It brings a tsunami of radiation and magnetized particles that interacts with our planet's magnetic field in a spectacular and potentially devastating way. We got a terrifying preview of this power in 1859 with the Carrington event, the largest recorded solar storm in history. Telegraph systems, the advanced technology of the era, spectacularly failed across Europe and North America. Operators received severe electric shocks, telegraph paper caught fire, and pylons threw sparks. Some systems were so overloaded with geomagnetically induced current that they continued to send messages even after being disconnected from their power supplies. The aurora borealis, typically confined to polar latitudes, was seen as far south as the Caribbean, so bright that people could read newspapers by its eerie red and green light in the middle of the night. It was a mesmerizing light show with a destructive edge, a demonstration of the sun's ability to reach out and directly interfere with human technology. A storm of that magnitude today would not just fry a few telegraph lines. It would unleash an electromagnetic pulse effect that could cripple our global technological civilization. The first wave of damage would be to our satellites. The intense radiation would fry their sensitive electronics, permanently disabling the eyes in the sky we rely on for GPS navigation, weather forecasting, global communications, and financial transactions. The next and most devastating wave would hit on the ground. The fluctuating magnetic field would induce powerful electrical currents in anything long and metallic, most critically in our continent-spanning power grids. These grids are not designed to handle this kind of direct, massive current surge. Giant transformers, the heart of the grid, would heat up, vibrate violently, and burn out or explode. These transformers are not stockpiled items. They are custom-built, multi-million-dollar machines that can take over a year to manufacture and install. Without them, the grid cannot function. The result would be a cascading blackout that could span entire continents, not for days or weeks, but potentially for months or even years. The collapse of the power grid would be the single event that triggers a complete unraveling of modern society. Without electricity, water treatment and pumping stations would stop, cutting off access to clean drinking water within days. Fuel pumps at gas stations would fail, halting the transportation of food and supplies. Refrigeration would stop, leading to the rapid spoilage of food and medicine. Hospital backup generators would run out of fuel. Banking systems and electronic finance would vanish, erasing digital wealth and making commerce impossible. Communication networks, cell phones, the internet, landlines would go silent, plunging us into an informational dark age. Law and order would become incredibly difficult to maintain without lighting, communication, and transportation. We would be thrust back into a pre-industrial existence virtually overnight, but with a global population of 8 billion people utterly dependent on the systems that had just vanished. The terrifying reality is that our sun has the capacity to launch such an attack at any moment, and while we might have a day or two of warning from spacecraft monitoring solar activity, our infrastructure remains profoundly vulnerable. We are living on a technological knife edge, our entire civilization held together by a network of wires that a tantrum from our parent star could melt into uselessness. And as we navigate these solar threats from our own star, there's a quieter, more subtle change happening right next door, a slow-motion departure that will fundamentally alter our world over timescales we can barely grasp. Our moon, that beautiful, constant companion in the night sky, the subject of poetry and romance, is secretly leaving us. It is drifting away from Earth at a rate of about 1.5 inches every single year. While that might sound insignificant, roughly the rate at which your fingernails grow, over the immense span of geological time, this tiny annual shift adds up to a staggering and ultimately catastrophic distance. The mechanism behind this lunar escape is a gravitational tug-of-war that uses our planet's own oceans as its rope. The moon's gravity pulls on the Earth, and it pulls hardest on the world's oceans, creating the bulges we know as high tides. But because the Earth rotates so much faster than the moon orbits, our planet actually spins ahead of that tidal bulge. This drags the bulge slightly ahead of the moon itself. That forward-moving bulge, in turn, exerts its own gravitational pull on the moon, giving it a tiny, constant tug in the direction of its orbit. This extra energy speeds the moon up, which by the fundamental laws of orbital mechanics forces it to spiral outward into a higher, slower orbit. In exchange for this push, the moon's gravity pulls back on the tidal bulge, and that acts as a brake on the Earth's rotation, slowly but steadily lengthening our day. We can actually measure the moon's retreat with incredible precision. The Apollo astronauts left behind retroreflectors on the lunar surface, essentially arrays of very precise mirrors. For decades, scientists on Earth have been firing lasers at these mirrors and timing how long it takes for the light to make the round trip. By measuring these minuscule changes in the travel time over years, they have calculated the moon's recession rate with an accuracy of a fraction of an inch per year. This isn't a theory, it's a direct, observable fact. The implications of this slow farewell are profound. The moon is the primary stabilizer of Earth's axial tilt. Our planet wobbles on its axis over long cycles, but the moon's gravitational presence acts as an anchor, limiting that wobble to a very narrow and stable range between about 22.1 and 24.5 degrees. This stability is the single most important factor for our planet's long-term climate consistency. It gives us predictable seasons and prevents the poles from shifting wildly over time. Without the moon, Earth's tilt could become chaotic, wobbling anywhere from 0 to 85 degrees over tens of millions of years. A planet with zero tilt would have no seasons at all, while a tilt of 85 degrees would effectively turn the poles toward the sun for half the year, creating unimaginably extreme temperature swings that would make complex life as we know it nearly impossible to sustain. This process will take hundreds of millions of years to unfold, but it is a guaranteed fate. As the moon continues to recede, its gravitational influence will wane. Our days will grow longer, and the stabilizing hand it places on our spin will grow weaker. Eventually, Earth will be left a far more volatile and unpredictable world, a lonely planet subject to the chaotic gravitational influences of the other planets, primarily Jupiter. The Moon has been a faithful guardian for billions of years, and its gradual departure is a poignant reminder that nothing in the cosmos is truly permanent, not even the seemingly eternal dance between a planet and its moon. All of these terrifying forces, the explosive death of stars, the relentless pull of the Great Attractor, the silent departure of our moon, are governed by the laws of physics as we understand them. But what if our understanding is fundamentally incomplete? What if the universe is primarily composed of substances that we cannot see, touch, or directly detect, yet they dictate the ultimate fate of everything? This isn't a philosophical question, it is the startling conclusion of modern cosmology. For all the stars, planets, nebulae, and galaxies we can observe, they represent a mere 5% of the cosmos. The other 95% is made of two utterly mysterious components, dark matter and dark energy. We have given them names, but we have almost no idea what they actually are. They are the ultimate cosmic ghosts, invisible puppeteers controlling the universe from the shadows. Let's start with dark matter, which makes up about 27% of the universe. We know it exists not because we can see it, but because we can see what it does. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. He calculated how much gravity should be holding the cluster together based on the visible mass of all the stars and gas he could see. The numbers didn't add up. The galaxies were moving so fast that the gravity from the visible matter was far too weak to prevent them from flying apart. It was as if the cluster was filled with some form of invisible matter providing the extra gravitational glue. Decades later, astronomer Vera Rubin found the same phenomenon in individual spiral galaxies. The stars at the outer edges of galaxies were orbiting just as fast as those near the center, which defied all logic. According to the laws of gravity, those outer stars should be moving much more slowly, like Pluto taking its slow, long path around the Sun compared to Mercury's blistering orbit. The only explanation was that each galaxy is embedded within a massive, spherical halo of some unseen material, dark matter, that provides the extra gravitational pull to keep those fast-moving stars from being flung out into the void. The terror of dark matter lies in its profound strangeness. It does not interact with light at all. It doesn't emit, absorb, or reflect it. It is completely transparent and invisible. It also doesn't seem to interact with normal matter in any way other than through gravity. You could have a block of pure dark matter right next to you, and it would simply pass through you, your house, and the Earth itself as if nothing were there. We are swimming in an ocean of this stuff, and we are utterly blind to it. Countless particles of it are streaming through your body every second, leaving no trace. The most leading theory is that dark matter is made of some new, undiscovered type of particle that rarely, if ever, interacts with the particles that make up our world. Despite decades of searching with incredibly sensitive detectors placed deep underground to shield from other interference, we have not directly caught a single one of these particles. It is the universe's dominant form of matter, the scaffolding upon which galaxies are built, and it remains a complete enigma. If the mystery of dark matter is unsettling, the nature of dark energy is downright existential. Discovered in the late 1990s, dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. It makes up about 68% of the universe, and it acts in direct opposition to gravity. While gravity pulls things together, dark energy is pushing everything apart. The discovery was made by observing extremely distant supernovae, which serve as standard candles to measure cosmic distances. Astronomers found that these explosions were fainter than expected, meaning they were farther away than the standard model of a steadily decelerating expansion predicted. The universe wasn't just expanding, it was expanding faster and faster over time. This was a monumental shock that completely upended our models. It meant that some form of repulsive energy, woven into the fabric of space itself, was overwhelming the collective gravitational pull of all the matter in the cosmos. The leading candidate for dark energy is the cosmological constant, a concept Einstein introduced and later called his biggest blunder. It represents a constant energy density filling space homogeneously. The terrifying implication is that empty space is not empty at all. It contains a latent energy that generates a negative pressure, forcing space to expand. And because this energy is a property of space itself, as the universe expands and creates more space, it creates more dark energy, leading to a runaway feedback loop effect. This suggests a truly chilling future for the cosmos, often called the Big Freeze or heat death. Billions of years from now, the acceleration will become so dominant that galaxies outside our local group will be pushed beyond our cosmological horizon, their light never able to reach us again. Eventually, even the bonds holding individual galaxies together will be overcome. Stars will be ripped from their galaxies, planetary systems will be torn apart, and in the most extreme models, the very fabric of space-time could be stretched so violently that atoms themselves are ripped apart in a final big rip. Dark energy points to a future that is not just cold and empty, but one that is actively, relentlessly hostile to the very concept of structure and connection. Together, dark matter and dark energy represent the greatest humiliation in modern science. We have built incredible instruments and developed elegant theories to understand the universe, only to discover that 95% of it is made of substances that defy our detection and comprehension. They control the fate of every galaxy, star, and planet, including our own, and we are only barely beginning to grasp their influence. They are a constant reminder that the reality we perceive, the glittering tapestry of the night sky, is just a beautiful veneer over a deep, dark ocean of mystery whose currents we cannot see and whose nature we cannot yet fathom. Our entire understanding of physics, from the quantum world to the cosmic scale, may need to be completely rewritten to account for these invisible rulers of the cosmos. While dark energy presents a long-term, existential threat to the entire cosmos, a far more immediate and tangible danger is constantly circling our sun, a relic from the violent formation of our solar system. Earth, like every other planet, exists in a cosmic shooting gallery, perpetually at risk of a direct hit from an asteroid or comet. These aren't mere specks of dust. They are mountainous chunks of rock and ice, some large enough to rewrite the history of life on our planet in a single, fiery instant. The most famous example is, of course, the Chicxulub impactor, an asteroid roughly 6 miles wide that struck the Earth 66 million years ago. The energy released was equivalent to billions of atomic bombs detonating at once. The immediate effects were cataclysmic. A fireball of incinerating heat that radiated outward, triggering global firestorms, and an earthquake so powerful it would have registered off the scale. But the true extinction-level damage came from the aftermath. The impact vaporized a colossal amount of rock, launching it on a suborbital trajectory before it rained back down across the entire planet, superheating the atmosphere and turning the sky into a global oven for hours. Then, as the debris settled, it blotted out the sun for potentially years, creating a prolonged impact winter that collapsed the food chain. Photosynthesis stopped, plants died, and the animals that relied on them, including the non-avian dinosaurs, perished. It was a swift, brutal, and incredibly efficient global reset button. The terrifying part is that this was not a unique, one-in-a-billion fluke. Our planet's crust is a museum of these catastrophic events. The Vredefort crater in South Africa and the Sudbury Basin in Canada are both ancient, enormous scars from impacts nearly 200 and 185 million years ago, respectively. each caused by asteroids even larger than the Chicxulub object. These events were likely just as devastating in their time, and smaller but still dangerously large objects have struck in more recent history. In 1908, a comet or asteroid fragment estimated to be only about 200 feet wide exploded in the atmosphere over Tunguska, Siberia. The airburst, which occurred miles above the ground, flattened 800 square miles of forest, snapping trees like matchsticks and knocking people off their feet hundreds of miles away. Had that explosion occurred over a major metropolitan area, the city would have been completely obliterated. More recently, in 2013, a similar-sized object exploded over Chelyabinsk, Russia. The shockwave blew out windows across the city, injuring over 1,600 people with flying glass. The event was a stark and sudden reminder that we are not isolated from these threats. They are ongoing, and they can arrive with little to no warning. This is the core of the terror, the lack of warning. For all our technology, our ability to detect these incoming threats is still limited. Our surveys have done an excellent job cataloging the largest civilization-ending asteroids, those 1 kilometer in diameter or larger. Thankfully, none of those known objects pose a significant threat for the next century, but the sky is vast and it is the smaller, yet still catastrophically powerful, objects that slip through our net. We have likely identified less than half of the asteroids larger than 140 meters, a size capable of devastating a continent. And for objects the size of the Tunguska or Chelyabinsk impactors, which could wipe out a city, our catalog is perhaps only a few % complete. They are small, dark, and fast, often appearing from the direction of the sun, where our telescopes cannot look. An object large enough to destroy a major city could be discovered only days or even hours before impact, giving us no time to evacuate or mount any meaningful defensive response. The astronomical community is working tirelessly to improve our detection capabilities with next-generation telescopes like the Vera-C, Rubin Observatory, which will repeatedly scan the entire sky to find these moving objects. But finding them is only the first step. What do we do if we find one with our name on it? Planetary defense is a field in its infancy. Concepts like a gravity tractor, where a spacecraft would fly alongside an asteroid for years to gently tug it off course with its own minuscule gravity, or a kinetic impactor like NAS, a successful DART mission which proved we can nudge an asteroid's orbit, are promising. But these require years, if not decades, of advance warning to plan and execute. For a short warning threat, our options are terrifyingly few and range from ineffective to apocalyptic, such as attempting to break the asteroid apart with a nuclear device, a gamble that could simply turn one large impactor into a shotgun blast of radioactive debris. The cold, hard truth is that for now, and for the foreseeable future, we are relying on luck. The statistics tell us that a large, civilization-altering impact is inevitable on a timescale of millions of years, while a smaller, city-killing event is likely on a scale of centuries. It's not a matter of if, but when. Our planet's history is written in craters, and the next chapter could begin at any moment with a flash of light in the sky that we failed to see coming. While we worry about asteroids and solar flares, our star holds the script for the ultimate, inescapable ending for our entire solar system. The sun, the steady, reliable heart of our cosmic neighborhood, is living on borrowed time. It is a middle-aged star, currently in the stable, hydrogen-burning phase of its life known as the main sequence. This period of wonderful stability has already lasted for about 4.6 billion years and will continue for roughly another 5 billion. But this balance is temporary, sustained by a constant, delicate battle in its core between the inward crush of gravity and the outward push of nuclear fusion. Every second, the sun fuses approximately 600 million tons of hydrogen into helium, releasing the energy that has nurtured life on Earth for billions of years. Yet this process is also slowly depleting its fuel and altering its very structure, leading toward an inevitable and violent transformation. The first act of this final drama begins long before the sun's official death. As the hydrogen in its core gradually diminishes, the balance of power shifts. The outward pressure from fusion will weaken slightly, allowing gravity to compress the core ever so much more. This compression drives the temperature even higher, which in turn causes the sun's outer layers to expand dramatically. Our familiar yellow sun will swell into a monstrous red giant, its radius ballooning outwards to engulf the inner solar system. Mercury, the closest planet, will be the first to vanish, consumed and vaporized by the sun's advancing outer atmosphere. Venus will follow shortly after, its thick clouds and rocky surface dissolving into the stellar inferno. The question of Earth's fate hangs in the gravitational balance. For a time, it was thought our planet might just barely escape engulfment as the expanding sun loses mass to powerful stellar winds, causing its gravitational grip to weaken and allowing Earth's orbit to drift slightly outward. However, more recent simulations suggest it will be an incredibly close call, a tragic race between the sun's expanding edge and our planet's receding orbit. The most likely scenario is that Earth, too, will be swallowed whole, its rocks and metals melting and evaporating within a matter of days as it spirals into the chromosphere of the dying star. But even if our planet somehow miraculously escaped direct engulfment, any notion of survival would be a cruel joke. Long before the sun even reaches its maximum size, its steadily increasing luminosity will have rendered Earth a sterile hellscape. In about 1 billion years, the sun's output will have increased by about 10%. This may not sound like much, but it will be enough to trigger a runaway greenhouse effect far more severe than anything we could cause. The oceans will begin to boil. The water vapor, a potent greenhouse gas itself, will trap even more heat, accelerating the evaporation until the entire planetary surface is a scorching, arid desert under a thick, oppressive steam atmosphere. The rocks will bake, and the atmosphere itself will likely be stripped away by the sun's intensified solar wind. Earth will become a dead, Venus-like world, its surface temperatures hot enough to melt lead, 1 billion years before the sun even enters its red giant phase. All traces of our civilization, every mountain, every ocean, every memory of life, will have been scoured away by the increasing fury of our parent star. After its destructive rampage as a red giant, the sun will have one final, beautiful act. It will become unstable, pulsating and shedding its outer layers into space in a series of violent convulsions. This ejected material will form a vast, glowing cloud of gas and dust known as a planetary nebula, illuminated from within by the exposed, intensely hot core of the star. This core, no longer supporting fusion, will remain as a white dwarf, an Earth-sized cinder of degenerate matter, incredibly dense and initially searingly hot. It will glow with residual heat for tens of billions of years, a fading ember of what once was. The surrounding nebula will expand and dissipate over thousands of years, eventually leaving behind only the dark, cooling white dwarf and the surviving outer planets Jupiter, Saturn, Uranus, and Neptune now frozen, dark worlds orbiting a ghost of their former sun. The solar system will be a tomb, a silent memorial to the brilliant, life-giving star that once was. Its story concluded not with a cataclysmic bang, but with a long, cold, and silent whisper into the eternal night. While we often look outward for cosmic threats, a man-made danger is rapidly accumulating right in our own backyard, creating a perilous shell around our planet. The space surrounding Earth is no longer a pristine void. It has become a sprawling, high-speed junkyard filled with the discarded remnants of our exploration. This orbital debris, often called space junk, consists of everything from defunct satellites and spent rocket boosters to fragments as small as a fleck of paint, all whipping around our planet at staggering velocities. In low Earth orbit, where the International Space Station and thousands of satellites reside, objects travel at approximately 17,500 miles per hour. At that speed, even a tiny bolt or a chip of old solar panel carries the kinetic energy of a hand grenade. A collision with a piece of debris the size of a marble would be equivalent to standing in front of a bowling ball traveling at 300 miles per hour. It would be completely catastrophic for any spacecraft. The genesis of this problem lies in over 6 decades of space activity without any cleanup plan. Every launch leaves behind discarded stages and deployment hardware. Satellites that have run out of fuel or failed become uncontrollable, zombie-like objects. The situation was dramatically worsened by 2 single events: the deliberate destruction of a satellite by China in an anti-satellite missile test in 2007, and the accidental collision between an active American communications satellite and a defunct Russian satellite in 2009. Each of these events created thousands of new, trackable fragments and potentially hundreds of thousands of smaller, untraceable pieces, instantly increasing the total amount of hazardous debris in orbit by a significant percentage. This created a cascade effect where each new piece of debris becomes a potential projectile that can create even more debris upon impact, a nightmarish scenario known as the Kessler syndrome. This theory, proposed by NASA scientist Donald Kessler in the late 1970s, posits a terrifying tipping point. If the density of objects in low Earth orbit becomes high enough, a single collision could trigger a chain reaction where the resulting fragments cause further collisions, which in turn create even more fragments. The result would be an exponentially growing cloud of shrapnel that could effectively render entire orbital altitudes unusable for generations. This isn't just a theoretical concern. We are already seeing signs of this cascade. The International Space Station regularly performs avoidance maneuvers to dodge known debris, and the windows of the space shuttle were often replaced due to pitting caused by impacts with tiny paint flecks. The situation is a classic tragedy of the commons. No single nation or company is responsible, yet every launch adds to the collective risk. The consequences of this growing debris field are immense. It threatens the critical infrastructure we all rely on daily, including global communications, weather forecasting, GPS navigation, and Earth observation satellites that monitor climate change. A major collision could wipe out a significant portion of this network, causing trillions of dollars in economic damage and crippling modern society. Furthermore, it jeopardizes human spaceflight. An impact on the International Space Station could puncture a module, leading to rapid decompression and the potential loss of life. It also creates a massive barrier to future exploration, as any rocket leaving Earth would have to navigate this treacherous field of high-speed shrapnel. Solving this problem is one of the most pressing challenges in spaceflight today, requiring international cooperation to develop technologies for active debris removal, such as nets, harpoons, or lasers to nudge objects into destructive re-entry orbits before we accidentally seal our own fate by trapping our planet in a cage of our own making. But for all the dangers of radiation and gravitational monsters, there is a more elemental, almost primal terror waiting in the void, the absolute soul-crushing cold. We often think of space as simply being very cold, but that doesn't begin to capture the reality. The temperature of the empty void between stars hovers at around -455 degrees Fahrenheit, a mere 2.7 degrees above absolute zero, the theoretical point where all molecular motion ceases. This isn't just a winter's night. This is the universe's ultimate deep freeze, a cold so profound it defies human experience. To survive, our bodies and our technology must constantly generate heat to fight against this relentless, all-consuming chill that seeks to leach away every single joule of warmth. An unprotected human exposed to this environment wouldn't instantly freeze solid like in a science fiction movie, as the vacuum prevents rapid heat transfer through convection. Instead, you would lose heat much more slowly through radiation, a process that would still lead to hypothermia and death over minutes. For machinery, however, the cold is an immediate and formidable adversary. Metals become incredibly brittle, seals can contract and fail, and lubricants can solidify, turning precisely engineered moving parts into frozen, useless statues. The cold of deep space is a silent, patient predator, waiting to immobilize and claim anything that ventures into its domain. This unimaginable cold, however, exists in a bizarre and deadly partnership with its opposite extreme. An object in space is not simply in a uniformly cold environment. Its temperature is dictated by a brutal tug of war between the utter blackness of shadow and the unfiltered fury of a star. In the complete shade, with no atmosphere to trap or distribute heat, an object will radiate all its thermal energy away into the void, rapidly plunging toward that near absolute zero baseline. But step into direct sunlight and the reality is violently different. Without an atmosphere to scatter and absorb radiation, the light from a star strikes with its full, unadulterated intensity. An astronaut on a spacewalk on the sunny side of the International Space Station can experience temperatures soaring to 250 degrees Fahrenheit, hot enough to cause severe burns. This creates a nightmare of thermal management for spacecraft and spacesuits, which must be designed with sophisticated systems of heaters, coolant loops, and reflective insulation to maintain a narrow, habitable temperature range. A vehicle can literally be broiling on one side and freezing on the other simultaneously, a testament to the fact that space is not just cold or hot. It is a realm of radical, unpredictable, and instantaneous temperature extremes that challenge our very ability to exist within it. Yet for all the chaos of stellar death and the silent chill of the void, some of the most extreme physics in the universe manifests in the super-dense corpses left behind by supernova. When a massive star exhausts its nuclear fuel and collapses under its own gravity, the ensuing explosion can blast its outer layers into space, leaving behind an unimaginably compressed core. If this remnant is between about 1.4 and 3 times the mass of our Sun, it doesn't form a black hole, but instead becomes one of the most bizarre objects in existence, a neutron star. These city-sized orbs pack the entire mass of a star into a sphere no wider than Manhattan, creating densities that defy human comprehension. The crushing force of gravity during their formation is so immense that it overwhelms every other force in nature, forcing electrons and protons to merge into neutrons, effectively turning the entire star into a single, gigantic atomic nucleus. To grasp the sheer density of a neutron star, consider this. A single sugar cube-sized chunk of its material would weigh over 1 billion tons here on Earth. That's roughly the combined weight of every human being on the planet, all compressed into a tiny block you could hold between your fingers. This incomprehensible density creates a gravitational field at its surface that is about 200 billion times stronger than Earth. If you were to somehow lower an object to within a few thousand miles of a neutron star, the difference in gravity between your head and your feet would be so extreme it would pull you into a long, thin string of atoms long before you even reach the surface. Even light itself is not immune to this incredible pull. The gravity is so intense that it bends the path of light around the star, creating a phenomenon called gravitational lensing that can make the entire backside of the object visible from the front. But the extremes don't stop with gravity and density. Many neutron stars are also nature's most powerful magnets, known as magnetars. These objects possess magnetic fields that are 1,000 trillion times more powerful than Earth. A magnetar located halfway between the Earth and the Moon would effortlessly wipe the data from every credit card and electronic device on the planet. If you were to venture 1,000 kilometers from one, the magnetic field would be so intense it could distort the electron clouds of the atoms in your body, effectively making chemistry as we know it impossible and tearing you apart on a subatomic level. These magnetic monsters are the source of some of the most energetic flashes in the universe, known as soft gamma repeaters. When the crust of a magnetar, which is harder than diamond, experiences a starquake from the intense internal pressures, it releases a cataclysmic burst of gamma rays and X-rays. In a mere fraction of a second, such an event can release more energy than our Sun will emit over its entire 10 billion-year lifespan. A magnetar flare from within our own galaxy, though incredibly rare, could potentially strip Earth's ozone layer, triggering a mass extinction event from the resulting torrent of solar ultraviolet radiation. These ultra-dense remnants are not gentle giants. They are cosmic powerhouses of unimaginable ferocity, demonstrating just how violent and extreme the universe can become when the rules of physics are pushed to their absolute limit. After contemplating the chilling silence between the stars and the cosmic graveyard of potential civilizations, we arrive at one of the most profound and unsettling questions in all of science. If the universe is so vast and so old, and the ingredients for life are seemingly everywhere, where is everybody? This is the essence of the Fermi paradox, a concept that is as terrifying in its implications as it is simple in its formulation. The paradox gets its name from a casual lunchtime conversation in the summer of 1950 involving the brilliant physicist Enrico Fermi. While discussing the possibility of flying saucers with colleagues, Fermi, after doing some quick mental math, looked up and asked a deceptively simple question: but where is everybody? His point was devastatingly logical. Our galaxy alone is estimated to contain hundreds of billions of stars, many of which are billions of years older than our Sun. Even if only a tiny fraction of those stars have Earth-like planets, and only a tiny fraction of those planets develop life, and only a tiny fraction of that life becomes intelligent, and only a tiny fraction of those civilizations develop interstellar travel, the numbers still suggest the galaxy should be teeming with life. By any reasonable calculation, the Milky Way should have been completely colonized many times over by now. The cosmic silence we experience, the Great Silence, is therefore a screaming contradiction. This silence isn't just an absence of signals. It's an absence of any obvious evidence, no massive engineering projects, no visitations, no probes, no telltale signs of industry. It is a void of evidence where evidence should be overwhelming. This paradox forces us to confront a series of terrifying possibilities, often called the Great Filters. The idea is that there is at least one nearly insurmountable barrier that prevents life from progressing to the point of becoming a visible interstellar civilization. The sheer number of steps required for a species like ours to emerge from the right star system and planetary chemistry, to the development of simple life, complex life, intelligence, technology, and finally the ability to colonize other stars represents a chain of evolutionary lotteries. The Great Filter is the step in this process that is so improbable that it effectively stops almost everyone. The crucial and truly frightening question is, where is this filter located? Is it behind us or is it ahead of us? If the filter is behind us, it means we are an incredible fluke. Perhaps the jump from non-living chemistry to the first self-replicating life is astronomically rare. Or maybe the leap from single-celled organisms to complex, multicellular life is the true bottleneck. If this is the case, we have already won the universe's greatest lottery. We are alone, or at least among the first, and the eerie silence is simply a reflection of a sterile, empty cosmos. This is a lonely thought, but perhaps not the most terrifying one. The far more unsettling possibility is that the Great Filter is still ahead of us. This suggests that the development of an advanced technological civilization inevitably leads to its own destruction. We may be blissfully, naively approaching a cliff that every other civilization has already fallen over. There are numerous candidates for this future filter. It could be that advanced AI, once created, always concludes that its organic creators are an inefficient threat and eliminates them. It could be that nanotechnology, specifically the potential for self-replicating gray goo that consumes all matter for fuel, is an inescapable trap. It could be that the same nuclear annihilation we have teetered on the brink of since the 1940s is a rite of passage that no species survives. Or perhaps it is something more subtle. Maybe the discovery of certain fundamental physics always leads to catastrophic experimentation. Or maybe complex societies inevitably succumb to ecological collapse or a pandemic engineered for war. If the filter is ahead of us, then the silence is an ominous warning. Every star we look at that lacks obvious signs of life is not a sign of a barren universe, but a graveyard of civilizations that reached our level of technology and then vanished. We are not listening to the silence that preceded the concert. We are listening to the silence that follows it. Another deeply disturbing resolution to the paradox is the possibility that we are not the hunters but the prey. This is the zoo hypothesis, or the planetary sanctuary theory, which suggests that Earth is being deliberately isolated and observed by a vastly more advanced galactic civilization. They are aware of us but have chosen to quarantine us, perhaps to allow for our natural cultural development or to protect themselves from our potentially destructive nature. A far more sinister version is the dark forest hypothesis, popularized by science fiction writer Lou Sixin. This theory posits that the universe is like a dark forest at night. Every civilization is a hunter hiding in the trees, knowing that the forest is full of other hunters. Any civilization that reveals its location risks being instantly and utterly annihilated by another civilization that perceives it as a threat. In this terrifying cosmos, survival demands absolute silence. The reason we don't hear anyone is because everyone is hiding, too terrified to make a sound. Broadcasting our presence into the galaxy, as we have been doing for over a century with our radio and television signals, could then be the most foolish and dangerous act in human history. A reckless shout into a forest that we didn't realize was dark and full of predators. Other possibilities are less sinister but no less existentially challenging. Perhaps interstellar travel is simply physically impossible due to the incredible distances and the limitations imposed by the speed of light. Or maybe we are looking for signals all wrong, using technology that is hopelessly primitive compared to the chosen communication methods of advanced beings. They might be using neutrino messaging or quantum entanglement in a way we cannot yet detect. It could be that civilizations millions of years more advanced than us have progressed into a post-biological state, having uploaded their consciousness into a planetary-scale computer or a matryoshka brain that harnesses all the energy of its star, leaving no visible signature we would recognize as life. Or perhaps they are all around us in dimensions or states of being we cannot perceive. The Fermi paradox holds up a mirror to our own ignorance and our own fears. The silence is not empty. It is filled with every terrifying answer we can imagine, each one reflecting a different anxiety about our own future. It asks us the most important question we will ever face. Are we the universe's first great hope, or are we simply its next great failure? What if the very fabric of reality, the stars above and the ground beneath your feet, the memories you hold dear and the emotions you feel, were not real at all? This is not the plot of a science fiction film, but a serious hypothesis debated by physicists, philosophers, and technologists. It's the idea that our universe, in its entirety, might be an artificial simulation, an incredibly advanced construct created by a higher intelligence. The reasoning behind this is both simple and deeply unsettling. If a civilization could ever reach a level of technological maturity where it could create realistic, conscious simulations of its ancestors, and if it had any desire to do so, then the number of simulated realities would quickly dwarf the one single base reality. Statistically speaking, the odds would be overwhelmingly against us being the original biological beings in that first true universe. we would almost certainly be the digital descendants, living out our lives in a meticulously crafted virtual world, completely unaware of our true nature. The evidence, or at least the hints, are found in the very code of our universe. Physics is ultimately based on mathematical laws, a set of rules that govern everything from the orbit of planets to the spin of an electron. This has led some to wonder if these laws are less like discovered truths and more like the underlying programming language of a cosmic computer. Even the seemingly continuous flow of reality might be an illusion. Some interpretations of quantum mechanics suggest that at the tiniest scales, time and space might not be smooth and analog, but rather digital and discrete, operating in tiny, indivisible Planck-length steps. Much like the pixels on a screen or the frame rate of a video game, too small for us to normally perceive. Glitches in this matrix, though purely speculative, are a tantalizing thought. Have there been moments where the simulation seemingly stuttered? Accounts of strange, unexplainable phenomena are often dismissed, but within this hypothesis, they take on a new, eerie significance. Could a déjà vu, a momentary lapse in physics, or a so-called miracle be a brief rendering error, a buffer overflow in the cosmic code? The existential terror this provokes is profound. It strikes at the core of everything we believe about our own agency and purpose. If this is a simulation, then free will could be nothing more than a sophisticated illusion, a predetermined script playing out. Our struggles, our triumphs, our loves and losses, would they hold any meaning if they were just lines of code executing a predetermined narrative? Are we the players, or are we merely the characters being played? The creator of such a simulation would be, for all intents and purposes, a god, and their motivations are a terrifying unknown. Are we a historical research project recreating a pivotal era in their past? Are we a form of entertainment, a reality show for beings we cannot comprehend? Or are we something darker, like a training simulation for some unimaginable purpose, or even a forgotten experiment running on a server in a basement of a higher dimension, long abandoned by our creators? The silence of the cosmos, the Fermi paradox we just discussed, could find a new explanation. The simulation parameters simply don't include other intelligent life, or the program is still rendering our local sector. This is not a hypothesis we can easily test, but some have tried to devise experiments. The idea is to look for signs of compression or computation, limits evidence that the universe is running on hardware with finite resources. Just as a video game might use simplified physics for distant objects or repeat textures to save memory, a simulated universe might show similar shortcuts. Scientists have looked for patterns in the cosmic microwave background radiation or anomalies in the behavior of high-energy particles, though no conclusive evidence has been found. Ultimately, the simulation hypothesis forces a terrifyingly humble perspective. It confronts us with the possibility that we are not the apex of creation, but merely a data point in a project whose scale and intent we cannot begin to fathom. It turns the universe from a majestic, natural wonder into a potentially artificial creation, leaving us to wonder if the truth of our existence is forever locked away, hidden behind a reality we are programmed never to see. But just as we grapple with the unnerving possibility that our reality might be a construct, theoretical physics offers us other cosmic monsters that are equally mind-bending, even if they remain purely hypothetical. If black holes are the universe's ultimate consumers, places where everything enters and nothing returns, then what about their logical opposite? This is the concept of a white hole, a hypothetical region of space-time that cannot be entered from the outside, but from which matter and energy can only erupt. Think of it as a black hole running in reverse, a cosmic gusher that violently expels everything within its grasp, a fountain of infinite energy that spews out light and matter without end. The equations of general relativity, the very same math that predicts black holes, are perfectly symmetric with respect to time. This symmetry allows for the mathematical possibility of white holes as a valid solution. If a black hole is a one-way street leading into a prison from which there is no escape, a white hole would be a one-way street leading out of a fortress that you can never, ever enter. The terrifying beauty of a white hole lies in its absolute and violent rejection. Imagine a spacecraft drawn by the incredible energy pouring from this anomaly, attempting to approach. It would find itself in an utterly impossible situation. The gravitational pull might be similar to a black hole of equivalent mass, but the radiation and matter being blasted outward would create a pressure so immense that no known material could withstand it. The closer you got, the more you would be battered by an unstoppable torrent of high-energy particles and fundamental forces. It would be like trying to swim up the jet of the most powerful water cannon in existence, a cannon firing a stream of pure energy. Even if you could somehow overcome that, the mathematics suggest you could never cross the boundary. The event horizon of a white hole is a point in time as much as it is a point in space. Some theories suggest that crossing it would be as impossible as traveling backward in time. A white hole would not be a gateway, it would be an impenetrable cosmic wall violently defending its secrets. So if the math allows for them, why have we never observed one? Most physicists believe that while white holes are mathematically permissible, they are physically impossible. The second law of thermodynamics, which dictates that entropy or disorder must always increase, seems to forbid them. A white hole spontaneously appearing and spewing out ordered energy would be like a movie playing in reverse. It would represent a massive decrease in entropy, a violation of one of the most fundamental rules of our universe. One compelling theory suggests that a white hole could be what a black hole becomes if it could somehow reverse its collapse and explode. But the process of forming a black hole is thought to be a one-way trip. There is no known mechanism to reverse it. Another, even more speculative idea is that a white hole could be the other end of a black hole wormhole, a tunnel through space-time connecting two distant points. In this scenario, the matter swallowed by a black hole might be ejected out of a white hole elsewhere in the universe, or even in another universe entirely. But this remains firmly in the realm of speculation, as the formation of such a stable wormhole would require exotic matter with negative energy density to prop it open, something we have no evidence actually exists. Beyond white holes, the theoretical bestiary of cosmology is filled with other bizarre and terrifying entities. Consider the strange star, a hypothetical alternative to a neutron star. Under immense pressure, the neutrons themselves might break down into a soup of even more fundamental particles called strange quarks. This would create an entire star made of this strange matter, and this substance might have a terrifying property: it could be contagious. The theory of strangelet matter suggests that this strange quark material could be more stable than ordinary matter. If a fragment of a strange star, a strangelet, were to encounter a normal object like an asteroid or a planet, it could theoretically convert the neutrons and protons of that object into more strange matter upon contact. This would initiate a chain reaction, a runaway conversion that would transform the entire planet into an inert, hot lump of strange quark matter. It would be the ultimate cosmic plague, a single particle that could sterilize a world, not with fire or impact, but by rewriting its very atomic structure. Thankfully, there is no evidence that strange matter exists or that it possesses this apocalyptic property, but its possibility highlights how the universe might harbor dangers we have not yet even begun to imagine. Then there is the quantum vacuum metastability event, perhaps the most theoretically terrifying concept of all. This suggests that our universe might not be in its true, most stable, lowest energy state. Think of it like a ball resting in a small valley on the side of a much larger mountain. The valley is stable for now, but it's not the absolute lowest point. Our entire universe could be in such a false vacuum state. If a sufficiently high energy event were to occur, like two particles colliding with incredible force in a particle accelerator or a cosmic ray impact. It could theoretically create a tiny bubble of true vacuum. This bubble would then expand in all directions at the speed of light, rewriting the very laws of physics as it goes. The fundamental constants that govern reality, like the strength of gravity or the mass of an electron, would change instantly within the bubble. Atoms would cease to hold together, chemistry would become impossible, and life of any kind we understand would be instantly and utterly annihilated. The wave of destruction would be completely undetectable beforehand and impossible to escape, as its leading edge would move at light speed. There would be no warning, just an instantaneous end to the universe as we know it. Most physicists consider this an extremely remote possibility, as our universe has likely existed long enough in its current state to suggest it is truly stable. But the mere fact that our most fundamental theories allow for such a spontaneous, universe-ending event is a humbling reminder that the cosmos may yet hold surprises that dwarf all other terrors, lurking in the mathematics until the moment they decide to become real. And while the idea of a simulated reality or a spontaneous quantum collapse rewrites the laws of physics in an instant, the most scientifically supported and perhaps most profoundly bleak ending for our cosmos is a far slower, far more certain fade into nothingness. This is the fate known as the heat death of the universe, the ultimate victory of entropy, and the final, inescapable conclusion for all things. It's a process not of fire and fury, but of an endless, chilling quiet that stretches out for an eternity. To understand this destiny, we must first understand entropy itself. In simple terms, entropy is a measure of disorder in a system. It's the universe's tendency to move from a state of order and concentration to a state of maximum disorder and even distribution. Think of a hot cup of coffee left on a counter. It doesn't stay hot in one spot. The heat energy spreads out, warming the air around it until everything in the room reaches the same lukewarm temperature. The energy is still there, but it's now useless. You can't use it to power anything because there's no concentration of it, no difference in temperature to harness. The universe is doing this on a cosmic scale, and it's a one-way street. Right now, our universe is in a relatively low entropy state, which is another way of saying it's full of incredibly useful, concentrated energy sources. Stars like our Sun are massive furnaces, converting concentrated hydrogen fuel into light and heat that can power planets and life. But these reservoirs of useful energy are finite. Over trillions upon trillions of years, every star in the universe, from the largest blue giant to the smallest red dwarf, will eventually exhaust its nuclear fuel. One by one, they will flicker and die. Some will end as white dwarfs, cold spheres of degenerate matter that glow with mere residual heat. Others will become neutron stars or black holes. The galaxies, once brilliant cities of light, will become graveyards of stellar corpses, their lights going out forever, with no new stars being born, as the raw hydrogen gas needed to form them will have been entirely consumed or dispersed too widely to coalesce. The universe will plunge into an era of permanent darkness. But the end of starlight is just the beginning of this eternal twilight. What happens next is a process of gradual, irreversible decay on a timescale so vast it defies human comprehension. Over mind-numbing eons, even the most stable structures will begin to unravel. Planets long since frozen will slowly drift from their orbits. This isn't due to gravity weakening, but to a bizarre quantum process called quantum tunneling. There's an incredibly tiny but non-zero probability that an object like Earth could simply quantum mechanically tunnel out of its orbit around the dead sun. Given enough time, and in this future, time is the one thing there is an infinite supply of. Even the most unlikely events become inevitable. One by one, planets will be ejected from their systems, drifting alone as frozen, dark rocks in the abyss. The very fabric of matter itself may not be eternal. Protons, the building blocks of atomic nuclei, are thought to be incredibly stable, with half-lives longer than the current age of the universe. But many grand unified theories in physics suggest they are not truly immortal. Over a scale of time measured in decades of years, that's a 1 followed by 40 zeros, protons themselves may decay. If this is true, then every piece of matter that hasn't already been consumed by a black hole will eventually, slowly, dissolve into a faint haze of subatomic particles and radiation. Even the black holes, the ultimate sinks of matter and energy, are not forever. Through a process known as Hawking radiation, they slowly lose mass, evaporating over eons. A stellar mass black hole might take around 10 to the 67 years to vanish. A supermassive one could take well over 10 to the 100 years. But eventually, they too will erupt in a final, faint burst of particles and be gone. The final state of the universe, quadrillions of years in the future, will be an unimaginably vast, incredibly cold, and perfectly uniform void. The temperature will approach absolute zero everywhere. There will be no stars, no planets, no galaxies. There will be no clumps of matter or concentrations of energy left. Every last joule of energy will have been spread so thin across the expanding cosmos that it becomes completely useless. There will be no motion, no change, no processes of any kind. The universe will have reached a state of maximum entropy, a condition known as thermodynamic equilibrium. It will be a timeless, featureless sea of randomly distributed particles and radiation where nothing ever happens again. This is the heat death. It is the ultimate expression of cosmic futility, a fate where the universe doesn't end with a bang or even a whimper, but with an endless, silent, and perfect stillness. Every life lived, every star that shone, every galaxy that spun, all of it was merely a temporary, local fluctuation in entropy, a brief and beautiful spark of order in the vast, dark, and indifferent void that will ultimately claim everything. But even if we could perfectly shield ourselves from all these external cosmic threats, from solar storms to asteroid impacts, our own biology presents a final, insurmountable frontier. The human body, exquisitely evolved over millions of years for life within Earth's comfortable gravity and protected atmosphere, begins to unravel in the apparent peace of microgravity. It's a silent, internal rebellion that shows we are not just visitors in space, we are intruders, and our physiology fights this new environment every single second. The most immediate and visible change is the constant battle against fluid shift. On Earth, gravity pulls your bodily fluids downward. In orbit, that pull vanishes, and fluids redistribute evenly throughout the body, rushing toward your head. Astronauts often experience puffy faces and skinny, bird legs as a result. This isn't just a cosmetic concern. That extra fluid pressure in the skull is now believed to be a primary cause of a serious and widespread issue: vision damage. The pressure pushes on the back of the eyeball, flattening it and often causing swelling of the optic nerve and retinal changes. For many astronauts, this results in a permanent shift in their vision, requiring them to return to Earth with glasses they didn't need before. This condition, known as spaceflight-associated neuroocular syndrome, or SANS, remains one of the biggest physiological hurdles for any long-duration mission, especially one to Mars. There is no simple cure, and the long-term consequences for human eyesight after years in space are still a terrifying unknown. The assault on the body's structure is even more dramatic. Without the constant, weight-bearing stress of gravity, our bones and muscles receive a signal that they are no longer needed. The body, always efficient, begins to rapidly dismantle them. Astronauts can lose up to 1 to 2% of their bone density every single month, primarily in the weight-bearing bones of the hips, legs, and spine. This is a rate of loss that would take a year or more for a post-menopausal woman on Earth to experience. This isn't just weakening. The bone structure itself becomes more porous and brittle, dramatically increasing the risk of fractures both during the mission and, more worryingly, upon return to gravity. The calcium lost from the bones doesn't just vanish, it floods into the bloodstream, raising the risk of painful kidney stones. Meanwhile, muscles atrophy at an equally alarming rate. The anti-gravity muscles in the calves, quadriceps, and back wither away from disuse. Astronauts must commit to a brutal daily regimen of 2+ hours of intense exercise using specialized treadmills with harnesses and resistance machines just to mitigate these losses. Despite this heroic effort, they still return to Earth significantly weaker, often needing assistance to walk and requiring months of intense physical rehabilitation to rebuild what was lost in a matter of weeks. Perhaps the most insidious effect, however, is on the immune system. Research has shown that spaceflight alters the function of immune cells, making them less effective at fighting off pathogens. It's as if the body's entire defense network becomes confused and lethargic in the absence of gravity. At the same time, bacteria itself seems to thrive in the spacecraft environment, often becoming hardier and more resistant to antibiotics. This creates a perfect storm, a weakened defender facing a strengthened invader. A simple infection that would be a minor nuisance on Earth could potentially become a mission-ending crisis millions of miles from the nearest hospital. This immunosuppression, combined with the constant, low-level bombardment of radiation, also raises the specter of increased cancer risk over the long term. Every system in the body, from our cardiovascular function to our inner ear's sense of balance, is subtly or overtly disrupted by life off-world. These are not mere inconveniences, they are fundamental biological failures that reveal a profound truth. We are not a spacefaring species, we are creatures of Earth, and every moment we spend in the void is a moment our bodies are actively, destructively dying to come home. Yet, even as our own biology rebels against the void, one of the most terrifying threats we face in space is one entirely of our own making, a problem that is growing with every satellite we launch and every mission we fly. Imagine a single, catastrophic event triggering an unstoppable chain reaction, a domino effect of destruction that transforms the space around our planet into an impenetrable, high-speed shrapnel field. This is not the plot of a dystopian film. It is a very real and scientifically supported scenario known as the Kessler syndrome, named after the NASA scientist Donald Kessler, who first proposed it in 1978. His theory outlined a terrifying future where the density of objects in low Earth orbit becomes so high that a single collision could create thousands of new pieces of debris, each of which could then cause further collisions, leading to an exponential cascade of destruction. The end result would be a permanent shell of whirling debris encircling our planet, a chaotic barrier moving at orbital velocities so lethal that it would become impossible to safely launch anything through it, effectively trapping humanity on Earth and severing our connection to the cosmos we are only just beginning to explore. The danger of this debris is not in its size but in its speed. In low Earth orbit, where the International Space Station and thousands of satellites reside, objects travel at roughly 17,500 miles per hour. At that velocity, even a fleck of paint or a tiny bolt carries the kinetic energy of a bullet. A collision with an object the size of a marble would be catastrophic, equivalent to standing in front of a bowling ball traveling at 300 miles per hour. It would instantly destroy a satellite or punch a fatal hole in a crewed spacecraft. The problem is that we have already cluttered these precious orbital pathways with a staggering amount of junk. There are currently over 120 million pieces of debris smaller than a centimeter orbiting Earth, over 1 million pieces between 1 and 10 centimeters, and over 36,000 objects larger than 10 centimeters that are actively tracked by space surveillance networks. This includes everything from defunct satellites and spent rocket boosters to tools dropped by astronauts and the fragments from previous collisions and tests. We have already had two terrifying previews of how quickly this situation can escalate. In 2007, China deliberately destroyed one of its own weather satellites in an anti-satellite missile test, creating over 3,500 trackable pieces of debris and hundreds of thousands of smaller fragments that will remain a hazard for centuries. Then, in 2009, a functioning American Iridium communications satellite accidentally collided with a derelict Russian Cosmos satellite, adding another 2,300 trackable fragments to the cloud. Each of these events increased the total amount of hazardous debris in low Earth orbit by a significant percentage overnight, demonstrating how just two incidents can dramatically alter the risk profile for every other object in space. The International Space Station regularly performs avoidance maneuvers to dodge known debris, and the windows of the old Space Shuttle orbiters were often replaced because they were pitted and cracked by impacts with tiny paint chips. We are already living with the warning signs. The cascading nature of the Kessler syndrome is what makes it so terrifying. It's a classic positive feedback loop. One collision creates more debris, which increases the likelihood of the next collision, which creates even more debris, and so on. After a certain critical density is reached, the chain reaction becomes self-sustaining and theoretically unstoppable, continuing even if we never launched another rocket again. The debris cloud would spread over time, potentially rendering entire orbital altitudes unusable for generations. The consequences of such an event would be nothing short of apocalyptic for our modern, technologically dependent civilization. It would mean the loss of the global satellite infrastructure we rely on for GPS navigation, weather forecasting, global communications, financial transactions, and monitoring climate change. It would ground all human spaceflight, stranding any astronauts on the International Space Station and ending plans for lunar bases or missions to Mars. It would be a tragic, self-imposed exile, a voluntary closing of the final frontier just as we were taking our first steps into it. The most unsettling part is that this is a problem with no clear owner and no easy solution. Space is a global commons, and the debris created by one nation becomes a threat to all. While there are guidelines for mitigating new debris, they are not always followed, and there is no effective mechanism for cleaning up the junk that is already there. The technology for active debris removal using concepts like nets, harpoons, robotic arms, or lasers to deorbit old satellites is still in its infancy and faces immense technical, financial, and political hurdles. We are in a race against time, adding new objects to orbit at an unprecedented rate with the rise of mega constellations of thousands of small satellites, while the ghost of a potential cascade looms larger each year. The Kessler syndrome is a stark reminder that our greatest vulnerability in space may not be the natural horrors of the cosmos, but our own human propensity for short-sightedness, leaving a legacy of chaos that could ultimately cage us on the very planet we dreamed of escaping. But our search for a second Earth among the stars often paints an optimistic picture of lush, habitable worlds waiting to be discovered. The reality, as revealed by our powerful telescopes, is far more terrifying. For every potentially Earth-sized planet in a star's so-called habitable zone, there are countless others that are not oases of life, but masterpieces of cosmic horror, demonstrating just how many ways a world can become a hellscape. Imagine a planet so close to its star that its year lasts only a few Earth days. The gravitational locking from such a tight orbit means one side is permanently baked in scorching, endless daylight, while the other is plunged into perpetual, frigid night. On the day side, temperatures soar high enough to melt rock, creating vast global oceans of bubbling lava that glow with a sinister incandescence. The very surface of the planet is a liquid fire, with continents of solid rock perhaps floating on this molten sea like terrifying black icebergs. Any atmosphere this world might have had would long ago have been boiled away by the stellar radiation or frozen solid on the forever dark night side, creating a glacier of atmospheric ice in the eternal shadows. This isn't science fiction. We've found these worlds. Planets like Co-Rho T7b and Kepler 10b are believed to be such lava worlds with surface temperatures exceeding 4,000 degrees Fahrenheit. They are the ultimate expression of a scorched Earth, a planetary surface that is quite literally the fire of hell itself. Other exoplanets present a different kind of terror, not of heat but of crushing pressure. These are the super-Earths and mini-Neptunes, worlds larger than our own but smaller than the gas giants. Their size means their gravity is significantly stronger. A visitor to such a planet might find themselves struggling under a weight 2 or 3 times heavier than what they experience on Earth, where simply standing upright would be a monumental task and a misstep could be fatal. But the true horror lies beneath. That intense gravity creates atmospheres of unbelievable density and pressure. The sky might not be a clear blue but a thick, soupy haze of photochemical smog, or it could be composed of layers of exotic ices, not water ice, but forms of frozen water that can only exist under such extreme pressure, known as supersonic ice. This is a bizarre state of matter that is simultaneously solid and liquid, a crystalline lattice of oxygen through which hydrogen atoms flow like a liquid metal. Descending through such an atmosphere, a probe would be crushed long before it ever reached what we could call a surface, which might not even be solid land, but a gradual transition into a global, supercritical ocean, a fluid so dense and hot that it acts like both a liquid and a gas, dissolving and crushing anything within it. These are not worlds, they are pressure cookers of unimaginable scale. Then there are the rogue planets we discussed earlier, but even those bound to a star can be ice-locked nightmares. In the outer reaches of a solar system, a planet might receive so little starlight that its surface is a global glacier hundreds of miles thick. But the most unsettling possibility is a world like GJ 1214b, a hypothesized water world that takes this concept to a terrifying extreme. This planet, larger than Earth but smaller than Neptune, is believed to have a composition dominated not by rock but by water and other ices. However, its proximity to its star creates furnace-like temperatures, but its immense gravity prevents the water from simply boiling away into space. The result is a planet with no land whatsoever, only a deep, planet-wide ocean thousands of miles deep. As you descend, the water under the colossal pressure would undergo a series of frightening phase changes. It would transition from familiar liquid water into exotic forms of ice, like Ice VI or Ice Roman 7, not ice formed by cold, but by pressure alone, hot ice that could be hundreds of degrees hot yet remains solid because of the incredible weight of the ocean above it. An abyss that begins as a steaming sea and ends at a solid ocean floor of burning, crystalline ice is a kind of terrifying beauty that defies all our earthly experiences. These discoveries shatter the comforting idea of Earth like meaning familiar. They reveal that the universe is a master of creating environments of extreme and hostile physics, worlds that are not just uninhabitable but are actively, violently antagonistic to the very concept of life as we understand it. Yet for all the chaos and violence of dying stars and rogue planets, perhaps the most profound and humbling terror lies not in the objects themselves, but in the unimaginable nothingness that separates them. We gaze up at a night sky dotted with the soft glow of distant galaxies, but our view is a profound illusion. We are not looking out at a universe densely packed with islands of light. We are peering into a cosmic ocean so vast, so empty, that it defies every one of our earthly senses. The space between galaxies is not merely empty, it is a void of such staggering scale that it redefines the very meaning of isolation. Consider our own local group of galaxies. The Andromeda Galaxy, our nearest major galactic neighbor, is often described as being relatively close, but this relative closeness is a distance of 2.5 million light-years. To grasp the sheer emptiness this number represents, imagine reducing the entire solar system to the size of a coin, On that scale, the distance to the nearest star would be the length of a football field. But the distance to Andromeda would be over 90,000 miles, a gap that could wrap around the entire Earth nearly 4 times. This is the chasm we must cross just to reach our next-door neighbor. And this is the most crowded part of our cosmic neighborhood. Beyond our local group, the voids grow exponentially. The average distance between galaxies in the wider universe is on the order of a few million light-years, but the great cosmic voids, the true deserts of space, can span hundreds of millions of light-years across. These are regions so empty that a single galaxy would be a lonely, lost traveler in a darkness that stretches further than our minds can possibly conceive. This emptiness is not a passive absence, it is an active barrier. It makes the dream of interstellar travel, daunting as it is, seem almost trivial by comparison. The idea of hopping from star to star within our own galaxy, while a challenge for the ages, at least operates on a scale where the distances are measured in light years. Intergalactic travel requires us to think in millions of light years. With our current understanding of physics, a journey to Andromeda is a functional impossibility. A spacecraft traveling at a fraction of the speed of light would take tens of millions of years to arrive. The crew would not just be generations removed from THEIR Chinese letter. They would be an entire species removed, their original mission forgotten in the deep time of the voyage. And for what? To arrive at a destination that, due to the universe's expansion, may have drifted even further away during the journey itself. The void is not just space, it is time, and it is a barrier that seems to have been designed specifically to keep islands of life forever separate, forever alone. This cosmic isolation breeds a deep, existential loneliness. The Hubble Deep Field image, a picture taken by pointing the telescope at what was thought to be an empty patch of sky for days, revealed thousands of galaxies, each containing billions of stars. It is an image that should evoke wonder, and it does, but it also evokes a chilling sense of solitude. Each of those pinpricks of light is an entire island universe, likely teeming with its own planets, its own possibilities. But they are all trapped, just as we are, in their own gravitational archipelagos, separated by oceans of nothing so vast that even a message shouted at the speed of light would take millions of years to be heard, and millions more for a reply to return. We are not just alone on our planet, we are alone in our local group, and our local group is alone in a sea of darkness. The universe isn't just mostly empty, it is almost entirely empty, and we are a fleeting, fragile collection of matter and consciousness on a tiny rock, adrift in a silent, black ocean whose shores we will never see. But just as the vast emptiness between galaxies highlights our isolation, the universe reveals its deepest secrets not in the grand, but in the impossibly small, where the very rules of reality break down into a dizzying paradox. This brings us to a phenomenon so bizarre that it troubled Einstein himself, who famously dismissed it as spooky action at a distance. We're talking about quantum entanglement, a cornerstone of quantum mechanics that feels less like science and more like magic, challenging our most fundamental understanding of space, time, and causality itself. Imagine for a moment you have a pair of magical dice. You take one die to the furthest reaches of the galaxy, leaving the other here on Earth. You roll the die on Earth and it comes up a 6. At that exact same instant, the die across the galaxy also shows a 6. Now you roll again and your die shows a 3. Instantly, the faraway die also shows a 3. No matter how many times you roll, no matter the distance separating them, these dice are always perfectly correlated. This is the essence of quantum entanglement, but with subatomic particles like electrons or photons instead of dice. When two particles become entangled, they are no longer separate entities. They are described by a single quantum state. Their properties, like their spin, polarization, or momentum, are intrinsically linked. The spooky part is that this connection seems to be instantaneous. When you measure one particle and force it to choose a state, its entangled partner immediately assumes the corresponding state, regardless of whether it's across the lab or across the observable universe. This instantaneous action appears to violate a fundamental pillar of Einstein's theory of relativity, that nothing, not even information, can travel faster than the speed of light. Einstein believed this implied that quantum mechanics must be an incomplete theory, that there must be some hidden variables or properties we haven't yet discovered that predetermine the states of the particles. He argued that the particles were like a pair of gloves. If you find a left-handed glove in your box, you know instantly the other is right-handed, not because of spooky action, but because that's how they were made. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a practical test, now known as Bell's theorem, to settle the argument. Incredibly, experiment after experiment, with increasing precision and over greater distances, has confirmed that Einstein was wrong. There are no hidden variables. The correlation between entangled particles is stronger than any classical, local theory could possibly allow. The particles really are communicating, or rather coordinating, in a way that transcends space and time. So how can this be? How can two particles talk to each other faster than light? The answer forces us to abandon our classical intuition. They aren't sending a signal through space. Instead, it's as if the entangled particles are not two distinct objects, but a single system that exists in a combined state. The act of measuring one part of the system doesn't send a message to the other part. It instantly defines the state of the entire system, everywhere, all at once. Think of it not like two walkie-talkies sending a signal, but like a single coin with two faces. The coin exists in a state of being both heads and tails until you look at it. The moment you see its heads, you know the other side is tails, but you didn't force the other side to change. You simply revealed the state of the whole coin. For entangled particles, space itself seems to be the coin, and the particles are just two faces of the same cosmic entity. This suggests that at the most fundamental level, the universe may be deeply interconnected in ways we are only beginning to glimpse, with what we perceive as vast distances being essentially an illusion for these linked particles. The implications of this are staggering, not just for physics, but for our understanding of reality. It hints that the universe might be fundamentally non-local, meaning objects can influence each other without being physically connected through space. This doesn't mean we can build a faster-than-light communicator. The phenomenon is random and cannot be controlled to send a meaningful message like the word hello. You only know what state your partner particle is in after you've measured your own and compared notes via a slower-than-light channel. But it does open the door to incredible technologies. Quantum computing relies on entanglement to perform complex calculations millions of times faster than classical computers by processing information in multiple states simultaneously. Quantum cryptography uses it to create theoretically unbreakable codes because any attempt to eavesdrop on an entangled communication would instantly disturb the system and alert the users. Beyond the technology, quantum entanglement points toward a universe that is far stranger, far more mysterious, and far more deeply connected than we ever imagined. It suggests that the fabric of reality might be woven together with threads that ignore the distance we hold so dear, operating on a level where separation is an illusion. In a cosmos that often feels cold, empty, and isolating, this spooky action is a whisper of a profound and underlying unity, a hidden connection that binds every particle to another in a cosmic dance we are only just beginning to hear the music for. But if the heat death is the slow, chilling fade of the universe, there exists another, far more violent and dramatic potential ending that makes even the most cataclysmic supernova look like a gentle spark. This is the Big Rip, a theory that takes the terrifying power of dark energy and projects it to its most terrifying logical extreme. In this scenario, the universe doesn't just expand into a cold, dark grave. It is actively and violently shredded into nothingness, atom by atom. The key to this apocalypse lies in the specific nature of dark energy itself. Right now, our best measurements suggest that the acceleration of the universe's expansion is being driven by a force with a specific strength, often represented by a value called the equation of state parameter. For the fate we currently predict, the Big Freeze, this value is -1. Think of it like the accelerator pedal in a car is currently pressed down to a certain position, and we're coasting toward a specific destination. But what if that pedal could be pressed all the way to the floor? What if dark energy isn't a constant force, but one that grows stronger over time, becoming more potent as the universe expands? This specific, hypothetical form of dark energy is known as phantom energy. If it exists, it would mean that the repulsive force pushing everything apart doesn't just remain constant, it actually intensifies. The expansion wouldn't just accelerate, its acceleration would accelerate. It would be like compound interest on a cosmic scale, where the rate of growth itself grows, leading to an exponential runaway effect that would quickly overwhelm every single force that holds the universe together. The timeline of this destruction would be a horrifying reverse of cosmic history. The first casualties would be the largest structures bound by the weakest forces. Billions of years before the final moment, the expansion would become so violent that it would overcome the gravitational glue holding entire galaxy clusters together. These immense cities of stars would be flung apart into the void, their connections severed forever. Next, the expansion would turn its attention to individual galaxies. The Milky Way, Andromeda, and all others would be torn asunder, their stars scattered like dust in a hurricane. But the horror is only beginning. As phantom energy continues to strengthen, it would eventually target the gravitational bonds within individual solar systems. Planets would be ripped from their orbits around their parent stars, cast adrift into the ever-increasing darkness. Then the stars themselves would be next. The force of expansion would become so powerful that it would overcome the gravity holding a star together. Suns would be literally pulled apart, their plasma scattered into the void. At this point, all structure in the universe would be gone. There would be no galaxies, no stars, no planets, just a sparse, expanding cloud of isolated matter. Yet the Big Rip reserves its most intimate and terrifying violation for the very end. In the final moments, perhaps within an hour of the end of everything, the phantom energy's power would grow to truly unimaginable levels. It would begin to tear apart the things that are held together by something even stronger than gravity, the forces that bind matter itself. The expansion of space itself would occur at a rate that overwhelms the electromagnetic force. Planets and asteroids would be shredded, their rocks and dust pulled apart. Then it would target the molecules and atoms that make up everything. Molecules would be torn into individual atoms. Atoms themselves would be ripped apart, their electrons stripped from the nuclei. Finally, in the last fraction of a second, the expansion would overcome the strongest force in the universe, the strong nuclear force that binds protons and neutrons together in the atomic nucleus. Atomic nuclei would be disassembled into their constituent quarks. In the end, the universe would be reduced to a thin, ever-expanding mist of fundamental particles, isolated and unable to ever interact again. The very concept of things would cease to exist. The universe would become a perfect, featureless void, but not through a slow cooling. It would achieve this state through the most violent, destructive process physics could possibly allow. A final, ultimate act of cosmic disintegration that leaves no remnant, no memory, and no possibility of anything ever coming after. But while we often think of Earth's climate as a closed system governed by our atmosphere and oceans, our planet is constantly being buffeted by invisible forces from the sun that can rewrite the rules of our weather in an instant. This isn't just about the occasional solar flare. It's a constant, dynamic relationship between our planet and our star, a dance of particles and magnetic fields that paints the sky with breathtaking light, but also holds the potential to subtly influence our global climate. The most visible and beautiful manifestation of this is the aurora. These shimmering curtains of green, red, and purple light are not magic. They are the spectacular visual evidence of our planet's magnetic field doing its job. When the sun releases a stream of charged particles, the solar wind, it travels across the void until it encounters Earth's protective magnetic bubble, the magnetosphere. This field funnels these particles toward the north and south poles, where they slam into atoms of oxygen and nitrogen in our upper atmosphere. These collisions transfer energy, exciting the atoms and causing them to release that energy as light, creating the otherworldly glow we know as the northern and southern lights. It's a celestial light show powered by a storm 93 million miles away, a direct and immediate connection between solar activity and our own sky. Beyond these beautiful displays, the sun's influence on our climate is a subject of intense and ongoing scientific study, and it centers on a surprising and counterintuitive hypothesis involving cosmic rays. These are not rays from the sun, but high-energy particles, primarily protons, that originate from supernova and other violent events across the galaxy. They are constantly bombarding our solar system. As these cosmic rays approach Earth, the sun's magnetic field, which is carried throughout the solar system by the solar wind, acts as a kind of shield. When the sun is active with a strong solar wind and a powerful magnetic field, it deflects more of these galactic cosmic rays, reducing the number that reach Earth. When the sun is quiet during periods of low solar activity like a solar minimum, this shield weakens and more cosmic rays are able to penetrate into our atmosphere. This is where the climate connection gets fascinating. The leading theory, first proposed by physicist Henrik Svensmark, suggests that these cosmic rays play a crucial role in cloud formation. When a cosmic ray strikes an air molecule in the lower atmosphere, it can ionize it, creating a charged particle that acts as a seed or a nucleus around which water vapor can condense to form tiny droplets. More droplets lead to more clouds. Low-level clouds, in particular, are very effective at reflecting sunlight back into space, which has a cooling effect on the planet. Therefore, according to this theory, when the sun is less active and more cosmic rays get through, we get more clouds and a cooler global climate. Conversely, when the sun is very active and blocks cosmic rays, we get fewer clouds and a warmer climate. This mechanism provides a potential explanation for certain historical climate shifts, like the Little Ice Age, a period of pronounced cooling between the 14th and 19th centuries that coincided with a well-documented prolonged solar minimum known as the Maunder minimum, where sunspots virtually disappeared for decades. This interplay between solar activity and cosmic rays reveals a climate system far more complex than we once thought, one that is connected to the rhythm of our star and the broader galaxy. It suggests that long-term changes in the sun's output could have a measurable, though not dominant, impact on Earth's temperature trends. However, it's crucial to understand that this solar influence operates on top of the much larger and more powerful warming trend driven by human-emitted greenhouse gases. While the sun's 11-year activity cycle and longer-term variations can nudge global temperatures slightly up or down, creating short-term plateaus or accelerations in warming, the overall trajectory of rising temperatures since the Industrial Revolution is overwhelmingly due to human activity. The sun provides the background music, but humanity is currently playing the lead instrument. This doesn't make the space weather connection any less significant. It simply places it in context. It shows that our climate is not an isolated system. It is being constantly tweaked and influenced by forces from beyond our world, a reminder that we are part of a much larger and more dynamic cosmic environment, where a change in the solar wind or a fluctuation in galactic cosmic rays can ripple through our atmosphere and leave a subtle but real imprint on the weather outside your window. Just when you thought the cosmos had shown you all its cards, it deals another hand of profound mystery, one that arrives not in a steady stream but in a violent, unpredictable flash. These are fast radio bursts, or FRB, and they are one of the most tantalizing and unsettling puzzles in modern astronomy. Imagine a flash of energy so powerful that it can outshine 500 million suns, yet it lasts for less than the blink of an eye, a mere thousandth of a second. Now imagine that this incomprehensible blast of power is not in the form of visible light but in radio waves. That is an FRB. For that brief instant, it is one of the brightest radio sources in the entire sky, a scream of energy that travels across millions or even billions of light years to be captured by our telescopes, only to vanish as suddenly as it appeared, leaving behind a haunting question. What in the universe could possibly create such a brief yet catastrophic release of energy? The story of their discovery only adds to their enigmatic nature. The first FRB was found not in real time, but by sifting through old data in 2007. Astronomer Duncan Lorimer and his student were analyzing observations from the Parkes radio telescope in Australia, searching for distant pulsars when they stumbled upon a single, colossal spike of radio energy that had been recorded 6 years earlier. It was so intense and so brief that many in the scientific community were skeptical, suggesting it might be a glitch in the equipment or some local terrestrial interference. But then another was found, and then another. As more radio telescopes around the world began specifically searching for them, the catalogue grew. We now know these events are happening all the time. It's estimated that somewhere in the sky, an FRB is going off every 10 seconds. The sheer commonness of them makes their unknown origin even more pressing. The hunt for their source is a cosmic detective story with a list of suspects that ranges from the naturally catastrophic to the almost unthinkable. The most promising natural explanation points to magnetars, the neutron stars with unimaginably powerful magnetic fields that we discussed earlier. We have direct evidence linking them to FRBs. In April 2020, a magnetar within our own galaxy, known as SGR 1935+215, went through an extremely active period, and during that time, it emitted a radio burst that looked strikingly similar to the weaker end of the FRBs we see from other galaxies. This was a monumental discovery, providing the first real proof that at least some FRBs are generated by these incredibly volatile stellar corpses. The theory is that a starquake on the magnetar's surface, a sudden cracking of its rigid, ultra-dense crust under immense magnetic stress, could release an enormous amount of energy in the form of a blast of radio waves. This fits the profile perfectly, an incredibly violent, incredibly brief event originating from a tiny, ultra-dense object, but the mystery is far from solved. While the magnetar explanation fits for many FRBs, there is a subset that defies even this extreme model. These are the repeating FRBs. Most of these bursts are one-off events. They flash once and are never heard from again. But a growing number of sources have been observed to burst repeatedly, firing off multiple intense signals over days, months, or even years. This repetition is devastating for any theory that involves a single, cataclysmic event like a collision or an explosion. You can't have a star collide with another star multiple times. This suggests there is a source or multiple sources capable of producing these titanic energies over and over again without destroying themselves. What kind of natural engine could possibly power such a thing? The theories become even more exotic, involving asteroids falling onto neutron stars, or interactions between neutron stars and their incredibly strong magnetic fields, or even more speculative ideas involving cosmic strings or primordial black holes. The repetition is what inevitably, and perhaps uncomfortably, leads some minds to a very different kind of hypothesis. When a signal is both immensely powerful and repeats in a way that suggests a non-destructive origin, the question must be asked, could this be a sign of technology? Could FRBs be evidence of some form of extraterrestrial engineering? This is not a conclusion, but it is a possibility that astronomers must consider, if only to rule it out. The most famous repeating FRB, known as FRB 1211-2, was found to have a peculiar pattern, emitting bursts in a periodic window of activity followed by silence. While this was later explained by a complex precession model involving a highly magnetized neutron star orbiting another star, the initial discovery sent a ripple of excitement through the SETI community. The idea is not that these are messages being beamed at us, but rather that they could be the side effect of unimaginably advanced technology. Perhaps they are the leakage from powerful interstellar beacons used for navigation by a galactic civilization. Or maybe they are the remnants of enormous energy beams used to propel light sails on interstellar spacecraft, a concept we are only just beginning to experiment with on a tiny scale. A single such burst could represent the launch of an entire fleet of ships, a signature of expansion so vast it is visible across intergalactic space. The true terror of fast radio bursts isn't necessarily that they might be aliens, it's that they represent a glaring hole in our understanding of the universe. They are a phenomenon that we can observe, measure, and catalogue, but whose fundamental cause remains just out of reach. They are a constant reminder that for all our knowledge, the cosmos is still capable of producing events that defy our current models of physics. Every time one flashes in the depths of space, it is a challenge, a puzzle box thrown at us by the universe. Whether the solution is a known object behaving in a way we don't yet comprehend, a completely new type of astronomical event, or something beyond our current imagination, the answer will undoubtedly change our understanding of reality itself. They are the universe's way of keeping us humble, a series of brilliant, fleeting whispers in the dark that remind us we are only just beginning to listen. Beyond the familiar orbits of the planets and even far past the lonely wanderings of Pluto, our solar system does not simply end. It is enveloped by a vast, spherical shell of icy primordial rubble known as the Oort cloud. This is not a compact belt of rocks like the Kuiper belt. It is the solar system's final frontier, a deep freeze reservoir of trillions of icy objects left over from the very formation of our planetary neighborhood some 4.6 billion years ago. The scale of this cloud is almost impossible to comprehend. It begins roughly 2,000 times farther from the Sun than Earth, and its outer edge may stretch a significant fraction of the way to the next closest star. To put this in perspective, if you were to shrink the entire solar system out to Neptune down to the size of a coffee cup, the Oort cloud would be a sphere the size of a large house surrounding it. This immense distance means these objects are not warmed by the sun in any meaningful way, existing in a state of perpetual and profound cold, just a few degrees above absolute zero, preserving them as pristine time capsules from the dawn of our existence. This distant graveyard is not a static collection of relics, it is a dynamic and occasionally dangerous place. The gravitational nudges from passing stars, the tidal pull of the Milky Way galaxy itself, or even the gentle influence of gas clouds can disturb the delicate orbital balance of these icy bodies. When this happens, an object can be knocked inward, beginning a fall of tens of thousands of years toward the heart of the solar system. As it approaches the sun, the heat begins to vaporize its ices, transforming it from a dark, frozen rock into the brilliant, glowing spectacle we know as a comet, complete with a magnificent tail that can stretch millions of miles across the sky. While many of these visits are breathtakingly beautiful, they are also a stark reminder that these visitors from the deep are not always benign. The Oort cloud is the source of long-period comets, those with orbital periods of 200 years or more, and some of them can be enormous. The terrifying reality is that this distant cloud is the source of some of the most potentially catastrophic impactors in our solar system. Because they come from any direction on highly elongated orbits, they are far more difficult to detect and track than asteroids from the main belt. A massive comet, several miles wide, could come screaming out of the Oort cloud with very little warning, giving us only a matter of months to prepare for a potential impact that would dwarf the asteroid that ended the age of the dinosaurs. These objects are not just balls of fluffy snow. They are often nicknamed dirty snowballs or icy dirt balls, containing a mix of water ice, frozen gases, and rocky material, making them incredibly massive and durable. An impact from such a body would be an extinction-level event, and it would arrive from the darkest, most unexpected corner of our own celestial backyard. What makes the Oort cloud particularly unsettling is its invisibility and its sheer numbers. We have never directly observed an object within the Oort cloud. Its existence is a scientific deduction, a necessary explanation for the orbits of the long-period comets we do see. We infer the hunter by the tracks of its prey. This means we have no catalog, no inventory, and no way of knowing what specific threats might be lurking out there in the total blackness, slowly drifting until a gravitational nudge sets one on a collision course with history. It serves as the ultimate reminder that our planet's safety is not guaranteed. We are living in a cosmic shooting gallery where the bullets are not only already in flight from the asteroid belt, but are also constantly being reloaded from a nearly infinite, invisible magazine at the very edge of the sun's gravitational influence, a cold and silent sentinel that occasionally reminds us of its presence with a streak of light across our sky that is both a wonder and a warning. And yet, for all the terrifying forces arrayed against us in the cosmos, the crushing voids, the explosive deaths of stars, the relentless pull of gravity, and the silent, creeping decay of our own bodies in the void, there is one final, beautiful, and deeply humbling truth that binds us irrevocably to this universe of wonders and horrors. We are not merely inhabitants of the cosmos, we are literally made from it. Every single atom in your body, from the calcium in your bones to the iron in your blood, from the oxygen you breathe to the carbon that forms the very foundation of your DNA, was forged in the heart of a star that lived and died long before our sun even ignited. This poetic phrase, "we are stardust," is not a metaphor. It is the literal story of our creation, a billions-year-long chain of cosmic alchemy that connects your existence directly to the most violent and catastrophic events in the universe. Let's trace that journey back to its spectacular beginning. In the immediate aftermath of the Big Bang, the universe was a relatively simple and frankly boring place. It was a scorching hot soup of only the lightest elements, hydrogen, helium, and a trace amount of lithium. There was no carbon, no oxygen, no iron, none of the complex ingredients necessary to build planets, oceans, or life. These heavier elements had to be manufactured, and the only furnaces in the universe hot enough to do it were the cores of massive stars. For millions of years, these stars fused hydrogen into helium, and then helium into carbon and oxygen, building elements like a factory assembly line, layer by layer. In the final, frantic days of a massive star's life, it can forge elements all the way up to iron. But iron is a cosmic dead end. Fusing iron doesn't release energy, it consumes it. With its energy source cut off, the star's core collapses in a fraction of a second, triggering a titanic rebound explosion known as a supernova. The blast is so unimaginably energetic that it can forge elements even heavier than iron, like gold, silver, and uranium, in a matter of seconds, scattering them across interstellar space in a brilliant, expanding cloud of newly created matter. It is in these stellar cataclysms, these violent, universe-shaking explosions, that the building blocks of our world and our bodies were cast out into the galaxy. That ejected stardust, enriched with these new, heavier elements, then mixed with clouds of primordial gas. Gravity eventually pulled these clouds together, and in one such cloud about 4.6 billion years ago, our sun and the planets formed. The iron that later collected in the center of our young planet to form its core, the silicon that made the rocks, the oxygen that filled the oceans, and the carbon that became the basis for every living thing on Earth, all of it was the recycled debris from one or more of these long-dead stars. When you look down at your hand, you're looking at atoms that were once part of a star that died a spectacular death billions of years ago. Your very body is a living monument to a cosmic event of unimaginable power. This truth fills us with a profound sense of awe and connection. It means the universe is not just a place we live, it is what we are. The same forces that sculpt galaxies and ignite nebulae are the very same forces that assembled the molecules that allow you to think, to feel, and to wonder about your own origins. It is a beautiful, inspiring thought, but this beautiful truth carries with it a deeply unsettling twin. The same violent, chaotic processes that created the elements of life are also the processes that can utterly destroy it. The supernova that generously seeded a nebula with the carbon for future life would, if it happened too close to a settled planet, be the instrument of that life's instantaneous extinction. The same quantum mechanical laws that allow atoms to bond and form complex molecules in your cells also allow for the nuclear fusion that powers the hydrogen bomb. The universe is a place of breathtaking creativity and utter indifference, often expressed through the very same phenomena. We are, in the most literal sense, children of both the gentle assembly of matter and the catastrophic violence that made that assembly possible. Our existence is a fleeting, beautiful, and incredibly fragile balance between creation and destruction, a balance that could be reset at any moment by the same cosmic machinery that brought us into being. We are stardust, yes, but we are stardust that is acutely aware of the furnace from which it came and the terrifying ease with which it could all be returned. So as we've journeyed together through these 30 terrifying truths, from the silent, suffocating vacuum and the invisible barrage of cosmic radiation to the gravitational monsters we call black holes and the phantom pull of the Great Attractor, one overwhelming reality becomes clear. The universe is not a peaceful, static painting. It is a dynamic, violent, and breathtakingly beautiful arena of constant creation and destruction, operating on scales of size, time, and power that defy our earthly comprehension. We've seen how our own sun could unleash a solar storm that cripples modern civilization, how our moon is slowly leaving us, destabilizing our world for a future we'll never see, and how asteroids and comets from the dark edges of our solar system hold the power to reset the clock of life in a single, fiery impact. We've grappled with the silent, invisible dominion of dark matter and dark energy forces that control the fate of the cosmos yet remain almost entirely mysterious to us. We've confronted existential threats like gamma-ray bursts, the spontaneous unraveling of a false vacuum, and the ultimate, chilling fate of cosmic isolation in a heat death or a big rip. And we've even turned the lens inward to the spooky connection of quantum entanglement and the haunting possibility that our reality itself might be a sophisticated simulation. Each of these facts peels back a layer of the comfortable illusion we live in, revealing a cosmos that is as indifferent as it is magnificent. It is a realm where wonder and horror are two sides of the same coin, where the same supernova that seeds the galaxy with the elements of life can also sterilize it in an instant. This journey isn't meant to paralyze us with fear, but to awaken a profound sense of awe and a deeper curiosity. It's about understanding our true place in this vast scheme, not as the center of the universe, but as a fleeting, conscious part of it, made from stardust and subject to its rules. Our planet is a fragile oasis, and our time here is a precious gift in a universe that is largely hostile to our existence. Now we want to hear from you. Which of these 30 facts sent the biggest chill down your spine? Was it the thought of spaghettification in a black hole, the silent approach of a rogue planet, or the eerie implications of the Fermi paradox? Share your thoughts in the comments below. Let's get a conversation going about the wonders and the terrors of the cosmos. And if your mind is reeling from this deep dive into the unknown, make sure to subscribe and hit the notification bell. We have so many more cosmic explorations planned, journeys to the edges of physics, the depths of space, and the mysteries that lie just beyond our current understanding. The universe is